Hello everyone, thanks for coming. My name is Emanuele Cozzi, I'm a PhD student at Eurecom, and today I want to present you our work, Understanding Linux Malware, done jointly with Mariano Graziano from Cisco Systems, Yannick Fratantonio, and Davide Balzarotti from Eurecom. During last 10 years, research community and industries put the effort in fighting Windows malware and building effective solutions in order to analyze them. So they built tools and they prepared the necessary skill set in order to study this malware for the Windows operating system. But recently, we started seeing malware for Linux, for the Linux operating system. And they are getting popular, more popular every day. They are widespread, they are running in devices we have all around on a daily basis. Also because Linux is running on a lot of different devices. Also smaller devices, IoT devices. So we need something to analyze this malware. For example, the Mirai botnet was used to disrupt major websites, or Erebus that was used to ask for huge ransoms, or even the CIA probably developed the Linux malware, Outlaw Country, to sniff the network data. But as I said, Linux is running also on tiny devices. These devices sometimes are poorly secured, given open access to attackers and malware authors. So we wanted to develop an analysis environment to dynamic analyze these files, and previous works only focused at the network level. So after building this environment, we wanted to consider all the behaviors that are proper of the Windows world or Windows malware, and we wanted to port these techniques to analyze this behavior to the Linux world. And this is challenging. After doing this, we finally are probably able to understand the characteristics of Linux malware, their behavior, also in comparison with respect to the Windows malware. So Linux is running on desktops, servers, but even on routers, security cameras, drones. And the biggest problem here is diversity. Diversity is the key problem because all these devices are deeply different. And let's assume we get an ELF binary. ELF is the standard executable format for the Linux operating system. And we want to analyze this binary, maybe also dynamically. So we start creating our analysis environment, maybe built on top of an Intel CPU. But we are not sure this ELF file will run, because Linux is also running on other architectures, other platforms, such as ARM, MIPS, Motorola, or SPARC. But OK, so we have this binary, we guess it's a Linux malware, so we install a Linux distribution. But the ELF file format is a standard also for other systems, such as BSDs and Android devices. But finally, we prepare our environment. We start installing libraries, for example, such as the glibc. And if we suppose that this file is dynamically linked, we are sure that it will require for some libraries at runtime. But here, we are not sure we installed the correct libraries, because this malware may use, for example, the uclibc instead of the glibc. Uclibc is a tiny C library specifically designed for embedded systems. And I wanted to give you a couple of examples about this diversity problem. So we may expect that most of the malware are statically linked. This is actually true, because we want to have portability at the library level. But when you statically link an ELF file, this file will automatically embed some wrappers, usually contained in the C library, to use the system calls. And it will interface with a specific system call table. But we are not sure that our system is using the same way to call system calls, or it's using the same system calls table. So we have portability at the library level, but probably our system is not compatible. It cannot run this malware. Or also, some of the samples we got have a mismatch between the virtual address and the physical address. And we know that nowadays Linux kernel is using the virtual address to run executables, to map these binaries. Instead, this malware is using the physical address. It wants to use the physical address to map some data in the process memory space. And here, in order to run this malware, we must know from which device this malware is coming from, because we have to recreate the right environment in order to run it. So we needed a solution to solve all this, to address all these challenges and try to solve all these problems. And we developed an analysis infrastructure. We created this infrastructure, you can see. And this was quite difficult. This is the result of endless iterations, because initially, we thought of creating this infrastructure, this pipeline, to answer some questions. But at the end, the answers the pipeline was giving to us, they've been used to readapt again this pipeline, to evolve it in order to analyze most of the malware we have. And through this pipeline, what we do is to analyze these ELF files, to extract meaningful information out of it. We also run some static analysis jobs, and then we finally rerun this malware dynamically, this Linux malware. So we collected data for 1 year, and we were getting 200 candidate samples each day. We were trying to filter out from this set of samples all the binaries for which we were sure it were built for Android or other systems, such as BSD. And finally, our dataset consists of more than 10,000 samples. Then we analyzed it, we inspected the ELF header to start answering some questions. For example, about the diversity problem. We wanted to check if all these samples we have in our dataset, they are really built to run on a lot of different architectures. And in fact, the distribution is quite high. But we saw that only 1/3 of the dataset is built to run on top of Intel architectures that are the processors we usually see on desktop or servers, is the most common one. Instead, half of the dataset is built to run on processors that are typically used on embedded devices, such as MIPS, Motorola, or SPARC. And this is an adversarial setting. Then, if we consider that the same ELF header can be used to trick analysis tools, the situation might get even worse. In fact, we saw that there are samples completely deleting the sections table from the ELF header, giving out what we call an anomalous ELF, because it's completely valid by specification, but it's still uncommon, since most of the standard compilers we use, they always produce sections table. But also, we defined a set of ELF that we call invalid ELF, because they are not valid by the ELF specification, but still, the Linux kernel is able to execute these binaries. And for example, we found that there are malware pointing the segments table, entries of the segments table beyond the file, or sections table beyond the file, or even trying to overlap one entry in the segments table with the ELF header. And these two categories of binaries are causing errors and problems on common analysis tools. For example, GDB, that is the de facto debugger for the Linux operating system, can be completely blocked if we just null some bytes in specific fields of the ELF header. Then we run AVClass, that is a tool to extract the most likely family name from a set of AV labels. And we did this to understand what are the classes of malware that we have today on the Linux operating system, if they are broad and a lot and all different with respect to the Windows malware. And in fact, we saw that we don't have only botnets. We also have ransomwares. We have also banking Trojan. Then we wanted to measure, for example, the entropy of this malware. We tried to collect metrics on the assembly code. We also wanted to check if these malware are using obfuscation at code level, or if they are using nasty tricks to slow down the analysis process or reverse engineering efforts. And we wanted also to check if they're using packers. Because on Windows, we have a lot of different packers, and they are all different, and some of them have a really high complexity. Instead of Linux, there are samples using packers, but we saw that almost all of them are using UPX. UPX is an open source packer, freely available, and what they do, instead of modifying the packing algorithm, they just apply some aesthetic changes such that the final binary will be still UPX packed, but it won't be automatically unpacked by the UPX tool, the official UPX tool. So here we have UPX on one side and some variants of UPX on the other side. What they're doing, for example, is to modify magic bytes or typical UPX strings, or they insert junk bytes. But then we saw that there is one malware family that is already using a custom homemade packer. Probably this is a trend for the future. Probably in the future we will start seeing more packers specifically designed for the Linux operating system. And finally, the most important part of the pipeline, that is the dynamic analysis stage. We prepared different sandboxes based on different architectures. We reconstructed different environments. And with these sandboxes, we wanted to run, finally, this malware to emulate their code and to collect some behavioral traces. To collect the traces, we used inside the sandbox a Linux facility already embedded in the Linux kernel that is based on kernel probes and user probes. We use kernel probes to trace the system calls the malware are executing to check the arguments they are passing to the system calls and the return value. And then we use the user probes to trace some functions on the user side, at the user level. For example, we instrumented the C library to trace functions related to strings or to memory. Finally, we have a behavioral trace. From this trace, we can understand if the malware really ran or if we got some problems. For example, it might need some specific files inside an environment to be executed without problems. Or this malware might need different libraries that we don't have. So we had to install these libraries. And here we enter the feedback loop because every time we had to prepare the sandbox. And we wanted to check some of the behaviors, and we saw that Linux malware are already performing tricks or applying behaviors specifically designed for Windows in the past. For example, they are applying anti-debugging tricks, or they have persistent strategies, or there is process injection. And these are a lot. I don't have time to go through all of them now, but to give you some examples, for example, deception. Malware wants to change the process name at runtime. They want to deceive the analyst. They are doing this on Linux. For example, they prefer to rename the process with common names of famous demons, such as SSH and Telnet. They use less suspicious name that might refer to user applications, or something more suspicious. They take random alphanumeric strings, or completely suspicious by just removing completely the process name. And also, they are doing evasion. That is the ability of the malware to detect the analysis environment. This is really common on Windows, and it's happening on Linux as well. What they do is to check the proc and sys virtual file systems to detect at least major virtualization and emulation solutions. They are also using another trick that is really simple, but at the same time really effective. They check if the file has been renamed, because they know that when we get our samples from our feeds, from other researchers, usually we will modify the name of this file with the hash of its data. So if the name has been changed, they may decide to suppress the original behavior partially or totally. And Linux malware are already leaving us funny messages if they check if they detected an analysis environment. For example, there is one malware family leaving us a message also completely wiping the hard drive. But what I've shown you so far is just the tip of an iceberg. There are a lot of tiny details, and for this, I really invite you to read our paper. For example, in the health header, there is a specific field to declare the application binary interface of the operating system. The Linux kernel is not using this field today, but there is one malware that is using this to achieve compatibility on Linux and FreeBSD by declaring the FreeBSD ABI in this field. Also, we had to prepare sandboxes to execute the malware under root and user privileges, because depending on the execution privilege, they might show different behaviors or adapt their techniques, for example, to achieve persistence. And then we saw process enumeration that can be used to evade dynamic analysis environments, but they're using it so far only to check if the system has been already infected and to kill previous infections of the same malware. And finally, we saw that there are samples still unstripped. This is unexpected, and probably the lack of motivation. They still don't want to strip their symbols because they know we are not really ready. To conclude, Linux malware are still in their infancy, but they're already using a lot of different behaviors and tricks. And analyzing an L file is quite difficult because Linux is running on diverse devices, from a really small thermostat to a really large server. And in order to analyze these ELF files, as of today, we must know from which device this ELF is coming from. We must know for which device this ELF has been designed in order to reconstruct the right environment to execute it. So I'm excited to announce you that today we release our analysis infrastructure as a free service. So head over that website. You can submit your sample, your health file. We will analyze it for you, and finally you will get back a report. And also on this website, you can find our raw results, the raw results of our paper, and the full dataset. Thank you.
So we have time for questions. Please, in the middle.
Tudor Dimitris from the University of Maryland. Very interesting work. You focused on the challenges that this diversity in terms of architectures and OSs poses for analyzing malware, right? For running it in a sandbox, right? So my question is, does this also present a challenge for the malware creators in the sense that on Windows you create the malware, it has a very broad sort of list of targets. So on Linux, is that also the case or not?
Yeah, I guess this is a challenge also for malware creators because they have to think of all these devices that are different. So if they want to achieve a broad panorama of execution, if they want to cover a lot of different devices, they have to think about this. They have to think that each device might run a slightly modified version of Linux, might run a different Linux distribution with a different environment, so they must know this, yeah. Thank you.
Hey, Tobias Ewig from TU Delft, and I was wondering if they're trying to evade detection by basically blacklisting everything that's detection. Aren't they basically missing out on everything that's hosted somewhere in some cloud, PAS cloud, SAS cloud, basically like half the Linux ecosystem by just focusing on CPEs?
Yeah, so you're asking me if they are trying to evade specific CPUs, sorry?
I'm actually just wondering if they're missing out on potential targets because most of the Linux servers we see out there are mostly virtualized. So if they're checking for is it KVM, is it XAN, is it VMware, they're basically missing out on all of these targets.
Yeah, it might be, because what we saw is that they check common hypervisors or common solutions. We actually found something that is specific for bigger systems, also used by bank industry. So they are general, but there are a couple of families that are already targeting specific systems.
Hey, Manuel Egele, Boston University. Thank you very much. This is very interesting research. So one thing I was wondering during your presentation is that you said that you had to prepare the sandbox with the correct libraries and so on and so forth. And I was wondering whether that is something that happens automatically in your tool or what the mechanism for that was.
So probably in the future we aim to do this completely automatic, but for now we were preparing the sandboxes manually. So we were getting the needed libraries from the health header and then installing these libraries manually. Sometimes it was not that easy because it was difficult to find the right library. But yeah, for now it's manual, but we aim to do it completely automatic, yeah.
Okay, so my question is now you have opened this big melon. What's the next step?
Yeah, next step is to continue on this. I mean, there is still a lot of work to do. It's still really difficult to analyze this malware as a one-shot solution. You get the binary, you analyze it, you are sure it will run, you will be able to collect the behavior. So, for example, the diversity, the fact that you must know from which device the sample is coming from. And in the future, probably, we want to see if there is something to understand automatically the device, the origin of this sample, and to reconstruct the environment automatically.
Okay, thank you very much.
Okay.
So let's thank our speaker again. And now it's time for lunch. Bon appétit, everybody.